This module of the Basic Guide to Tree Felling is meant to cover the situation where it is felt that a bit more than wedges will be needed, and the tree will need to be pulled down.
Ropes can be designed to have little stretch, in which case they are referred to as static ropes. They can also be designed to have a lot of stretch, in which case they are referred to as dynamic ropes, or for our purposes, energy-absorbing ropes. Stretchy ropes are best for tree rigging work, where the rope will have to catch a heavy limb that has just been cut from high in the tree. Because the rope's resistance increases gradually as it stretches, such a rope will gradually slow and stop the fall, as compared to a static rope that would experience a very powerful jerk when the line goes taut.
The very high, very brief impact load would be more likely to snap the rope than if the load was accepted gradually. Here, the term gradual is relative, as the whole thing takes place in probably less than a quarter of a second. When it comes to pulling down a tree, however, we want a rope that will stretch as little as possible.
The biggest reason is that we want to minimize the amount of work required to exert the necessary force. Let's imagine that the force we need to generate in the rope is 150 pounds, and that our rope extends 100 feet to the tree. Let's also imagine that we have one rope that will stretch 15% before it exerts that tension, and another rope that will stretch only 2% before reaching that tension. In the first case, we will have to pull 15 feet of rope to us, as its resistance grows steadily to 150 pounds. In the second case, we will only have to pull 2 feet of rope to us, as its resistance grows to 150 pounds. Since work is the product of force times distance, the stretchy rope will require us to do 7.5 times as much work to reach the 150 pounds of tension. Another reason we want to use a static rope has to do with the amount of tension increase we can induce in the taut rope by pulling it sideways. We will explain that in more detail later.
A third reason we don't want a stretchy rope has to do with the disaster situation where we've pulled the rope enough to cause it to rupture.
This chart shows some of the stretching that common rope types can experience when pulled to 20 and 75% of their breaking strength. Let's imagine that we are using a nylon rope stretching 100 feet to our tree. The 42% indicates that the rope will stretch by 42 feet by the time it reaches 75% of its ultimate tensile strength. We can extrapolate to estimate that the rope will break when it is stretched by 50 feet. Let's further imagine that the rope is 3/8 inch nylon with a minimum breaking strength of 3,240 pounds and a weight of 3.6 pounds for that 100-foot length. With our bad luck, we will have used a strong winch to get it to fail at 3,240 pounds of tension, and the rope will snap at the tree and begin to fly back at us. As the calculations show, the stored energy due to the stretch will have the rope flying back at us at around 800 miles per hour, over Mach 1. Air resistance will bring that down some, but the risk of injury will still be great. In most cases, you will want a minimum of 150 feet of rope. So we go to our local hardware store in search of a reasonably strong but inexpensive rope. The pretty blue 3/8 inch polypropylene rope catches our eye at just $10 for a 100-foot length. It has a working load limit of 244 pounds, but we can't pull that hard anyway. We'll grab 2 bundles so we can tie them together to get our 150-foot length. If we're lucky, somewhere on the package it will warn us that doing so reduces the strength up to 50%. This particular packaging also states, "Never stand in line with rope under tension." We head home with $20 worth of rope, about the minimum we should spend to manually pull down a tree. Now let's say we want a better margin of safety and a slightly less stretchy rope. If we're lucky, our store carries half-inch double braid polyester rope. Its maximum load is way up to 1,900 pounds. Unfortunately, that comes at a cost of $1.99 per foot, so our 150-foot rope is now going to cost us nearly $300. This just started getting serious. If we want to get a bit more serious, we can go to the internet and order from an arborist supply house. We should be able to find some good static rope there, such as some 5/8-inch HTP static from Sterling Rope. That rope has a minimum breaking strength of 13,000 pounds and stretches only 1.8% when stretched to its working load limit of 1,300 pounds. At $250, it is a big improvement over the polyester.
Finally, we can get to pulling. The video on back leaners contains some cautionary notes about how pulling ability was often overestimated and the force required was often underestimated. Anytime the pull required is more than what a standing person or several standing persons can provide, a good strong anchor point is needed, preferably the bottom of another tree. Assuming we have a second tree at a favorable location to be a good anchor point, we want to tie our rope around it as tightly as possible. Bracing against the side of the tree, we wrap around and over the rope, pulling it back towards the tree, which further shortens the length. Then we come around the tree again, and we have to tie that off. With only the bight to work with, I usually find 2 hitches is sufficient. Our rope will now have as much tension as we can provide with a straight pull. Now it's time to consider doing some side pulling.
The side pull does 2 things. It lets us significantly increase the tension in the pulling rope, and it lets us adjust the direction of pull to be more in line with the direction we want. We can actually calculate how much tension we can add with a secondary pull. As a first step, we have to determine spring constants for the stretchiness of the ropes. We use Hooke's law, F equals Kx, to determine K, the spring constant. For our first case, let's assume we have a pretty strong nylon rope, 5/8 inch in diameter, with a breaking strength of 9,350 pounds. Nylon and polypropylene ropes are fairly stretchy. On average, they will stretch 20% when they are stressed to 20% of their breaking strengths. For a 100-foot rope, X will be 20 feet, and the force needed will be 20% of 9,350, or 1,870 pounds. Since K equals F divided by X, the spring constant for this particular rope will be approximately 93.5 pounds per foot. If we consider a 5/8 inch static rope, we find that its spring constant is 333 pounds per foot, approximately 3.5 times stiffer. Assuming we can put 150 pounds of tension into our first rope and tie it around an anchor tree 100 feet away from the tree we wish to pull down, next we can tie a rope to the middle of the first one and pull it sideways with the same 150 pounds of pull. Those of you who are really interested can stop the video and go through the math, but The bottom line is that this side pull will add an additional 151.6 pounds of tension to the first rope. If we repeat this with the same size rope, but use a static line with little stretch, such as a Sterling HTP static, and apply the same 150 pounds of primary and secondary pull, we get 271 pounds of additional tension, almost 80% more of an increase than with the stretchy nylon rope.
There are actually two parts to the stretchiness of a rope. One is the material itself and how the rope is built. The other part has to do with the relationship between the strength of the rope and the amount of pull being applied to it. Let's take a look at a much smaller rope, say the 3/8 inch polypropylene that we can buy for under $20 for a 100-foot length at many hardware stores.
While how the rope is built can improve the breaking strength, most such ropes claim a breaking strength of 900 pounds. Using that as our main rope and running through the numbers again, we find that our 150-pound sideways secondary pull only increases the primary tension by around 40 pounds. The reason for this is that the rope stretches significantly more, and when it is pulled farther out to the side, the primary tension is fighting your secondary pull more.
The bottom line on the side pull method is that you can use it to significantly increase your primary pull if you've got a strong rope, particularly if it's made from a non-stretchy material. As a less expensive alternative, we could use a cheaper rope and resort to using pulleys. As of January 2014, it was fairly easy to get half-inch rope pulleys in most hardware stores. This one has a 650-pound rated capacity and only cost $11. Between a strong rope and a good pulley, the price may start getting up around $500. For most people, those prices will separate the homeowner from the professional. So let's go with either this half-inch polypropylene or a half-inch nylon rope. For nylon, the typical capacity will range from around 4,000 to 7,400 pounds, with a working load limit of 500 to 700 pounds. This half-inch polypropylene lists its load limit as 244 pounds.
This figure illustrates a basic pulley setup. Once we tie the main rope to the trunk and tie our second rope around our anchor tree, we can begin to pull. Assuming we can exert a 150-pound pull, our pulley will exert 300 pounds of tension on the main rope and on the tree. Rather than being satisfied with just 300 pounds of pull, we can tie a second pulley to our second rope and put our third rope through that pulley. When we pull with 150 pounds of force on our third rope, our second pulley puts 300 pounds of tension into both legs of our secondary rope, which in turn puts 600 pounds of tension into our main rope. Note that these 600 pounds of tension are being passed through our first pulley, which has a rated capacity of only 650 pounds. While our ropes may have a significantly higher capacity, we don't want to overstress and break our pulley. Not only would we be out $12, we would have an angry pulley coming back at us trying to get even. If we need more pull, we should not add a third pulley into this system. Rather, we should duplicate the system, adding another anchor point. Unless our original anchor point is stout, we should try to avoid tying both systems to the same tree.
Once we get to a situation where we need to exert that much force, we probably should have started out with a chain and winch in the first place. The next video in this series, Pulling the Tree Down with Chain, will look at some of the equipment, its capabilities, and its use.